Okay, so what I wanted to say is that if we consider the doubly closed shell nucleus plus minus 1 nucleon, then the entire, since this doubly closed shell nucleus is a very good inert core, so the low energy spectra, okay, it will be as a result of the excitations of the single nucleon over here, right? Let us consider again an example of 17 oxygen, so which is just the good old 16 oxygen core plus a single neutron. This single neutron will go to 1d 5 half level, right? So our to be level scheme ta jodi hum dekhi, so 1s half, 1p3 half, 1p half, 1p5 half, then 2s half, then what? 1d3 half, right? Any questions? Kichu na? ठीक है तो? Now what? Yes. So this is what I am saying. For 17 oxygen, now you can see much better. 17 oxygen. So these are all fields. 1, 2, 3, 4. Again, this is field. So this is my. This is basically the corresponds to the inert core of 16 oxygen core, right? Inert core. Now this single neutron, it goes to this 1d5 half. Fine. So what's the ground state? Spin parity. What will it be? It will be just, yes, the speed parity will be just 5 by 2 plus. So this is the excitations. Okay, next, where can it go? It can go over here, right? So the first excited state, what can it be? It will be half plus. And what is the energy gap? How much? How much energy? The energy will be same. So if this gap is say epsilon 1, then this gap will also be epsilon 1. I am just explaining this doubly closed shell nucleus plus 1 nucleon excitation spectrum. Next, second excited state, it can go to here, right? So what's the possible? It will be 3 by 2 plus, right? And so if this one is epsilon 2, so what's the energy? The energy will be basically epsilon 1 plus epsilon 2 energy at excitation. Understand? So this is how we basically explain the excitation of the level scheme. Now the only thing very important is that during this very low energy excitation, this core doesn't take part, so it is inert. But if I consider much higher excitation energies, then it will also consider, the core will not remain inert and core will also be excited. So there can be also these levels, they will be going up, and we will be having more complicated scenarios like 3 neutrons, in some j is equal to 5 half, in some j is equal to 9 half, and so on and so forth. And then you have to do again the M scheme calculations. So this is how the things work. Now let us consider the case for doubly closed shell nucleus plus minus 2 nucleon. So this is our case. We have just considered 18 oxygen. Again 16 oxygen plus 2 neutron. Now in that case, what will happen is that you see something interesting happens now. Till now we were considering only one nucleon. A single nucleon outside an inert core, it doesn't interact with any other nucleon if I am considering the core to be inert. But right now I am considering 2 nucleons outside the core. So there is a possibility of interaction between the two nucleons. But again, you will say, sir, when we started considering or solving this nuclear many-body problem, the first thing that we did was assumed that the entire residual interaction is 0. Remember when we did the calculation last day, the two-body operator minus one-body operator, we approximated it to be 0. That means residual interaction is 0, which means indirectly that the two nucleons, they are non-interacting. They don't interact with each other. However, let us do a test. Okay. The test is like that. Say 18 oxygen. Okay, 18 oxygen. Now, what can we do in this case for 18 oxygen? Let me rub this part. So again, it will be 16 oxygen core plus the two neutrons. They will be in this 1d fiber. Okay, two neutrons in 1d fiber. ठीक है. Next is again 2s half, and then we have what? 1d 3 half. Any questions? No questions. High energy अभी जेटा बोलना, you will have to consider the coupling as well. If it goes to high energy. Now see what happens over here. You have just seen that two neutrons in 1d 5 half, they can have total speed what? J is equal to 0 to 4. Similarly for S, the total J will be 0. Again for J is equal to 3 by 2, the total J will be 0 and 2. Right? ठीक है sir? Fine. Now, two things important. In this case, here you see, in 1d 5 half, we can have J is equal to 0, 2 and 4. Fine. Now, interestingly, these three states, J is equal to 0, 2, 4, they should be degenerate or non-degenerate. You tell me. So, the question is this, two neutrons with J is equal to 0, 2 and 4, will they have same energy or not? Question. Follow. তুমি বলো ওদের সেম এনার্জি থাকবে কি না? Till now, in this entire interaction, in this entire discussion, have I ever considered about anywhere residual interaction? I have not considered anything. So what does this mean? There is nothing in our model which will be able to distinguish these three states. So this means that our model will predict that the three states will have same energy. But experimentally, we observe 0 to 4. There is a splitting. So experimentally, we observe a splitting. So this is theory, same energy, and different energy. This is from experiment. So what does this mean? This means that presence of residual interaction. Right? This means the presence of residual interaction. In fact, I will show you just now, after a few minutes, that we will consider a delta type residual interaction. Delta type residual interaction. And there you will see that because of this delta type residual interaction, there will be a shift in the total energy. It can be done, these calculations can be done using perturbation technique, and the shift will be very interesting. The shift will show you that there will be a J dependent term, and as a result there will be splitting between these three J values. What I am saying is that I will show you just now that considering the simplest possible residual interaction, a delta type residual interaction, we can show that in the entire energy calculation there will be a shift as a result of this delta type residual interaction, and the shift will depend on a J term, and as a result we can explain this experimental splitting. Okay, so this is one of the artifacts of residual interaction, one of the proofs of the presence of residual interaction, and this is basically the pairing interaction. You will see that this J is equal to 0 term is actually much bound compared to 0 and 2 and 4. And why is this so? What happens for J is equal to 0? For J is equal to 0, what happens is that the two neutrons, two nucleons, they are moving in the same orbit but in opposite directions, right? Same orbit in opposite direction. So there is maximum overlap between them. এটা একে অপরকে এই রকম করে ঘুরছে যে different types, they are seeing each other, at least if you think classically, they are seeing each other twice in the same orbit. So this means maximum overlap, right? Next, this is for J is equal to 0. Maximum overlap means more bound. Now for J is equal to 2, what will happen is that this is for J is equal to 0. For J is equal to 2, there is some angle between the two of them. So the overlap decreases, and as a result the corresponding energy is also less bound. For J is equal to 4, the angle is even more for J is equal to 4. And so there will be, so what will happen? You see the planes. First it was like this, next it was like this, next it was like this. So overall the overlap is less. Remember, we are talking about quantum mechanics. Everything is regarding overlap, wave functions. The whole matrix elements game, it is regarding overlap. Car সাথে car বেশি overlap. More overlap means more interaction. It can be bound, it can be unbound, but the moral of the story is more interaction. Okay? Right. Now in this case it will be more bound. So this is one of the manifestations of residual interaction. So one of manifestations of residual interaction, and this is basically this J is equal to 0 case is pairing interaction. The strong energy, we call this is the result of pairing interaction. Now we are giving a name for this particular type of residual interaction. Okay, now let me give you some other example as well. So this is one of the manifestations. There are other manifestations as well.
So one
of the manifestations of residual interaction. Now let me write down, let me show you something more. This 18 oxygen is a very nice example. It actually shows you that two very interesting possible manifestations of configuration of residual interaction. This was the first one. The second one, look over here. We can have 0 in 3 possible ways, right? Now you see, the arrangement of nucleons in each particular orbit is basically a configuration. So we can have one configuration like this, J is equal to 0. Another configuration we can have some excited state where this will be J is equal to 0. Yet another configuration where this will be the J is equal to 0. Right? Now you will say, sir, this is little bit higher. This is also little bit higher. So if I use the theory and see, you will see that these are the 3 0 plus. Right? But interestingly, you will not be able to explain the experimental spectrum using these values. The experimental spectrum will be something very different. It is like this. The experimental spectrum. This is theory, non-interactive. And this is, of course, experimental means they are interacting. and the result of residual interaction is over there. Okay, so this is 0 plus, this is 0 plus, this is 0 plus. Now how do you solve that? Tell me, how do you explain this thing? How can we explain this thing? This is theory, this is experiment. This thing can only be explained through configuration mixing. What is that? The thing is that I just told you that every possible arrangement of nucleons in a nucleus corresponds to a configuration, right? So we have got 3 configurations. Now, if the residual interaction causes these 3 0 plus to mix among themselves, then as a result of the mixing of this configuration, previously this is a pure configuration case, no mixing, but the residual interaction which we have been neglecting till now, it can mix the 3 pure configurations, and as a result we will get something like this. I will show you later on mathematically that as a result of the residual mixing between the configurations, what happens is that one of the states always becomes more bound and the others become less bound. Let me tell you, generally, had it been a n-level mixing, this is just an example of say 3-level mixing. 3-level mixing problem. Now, if we have an n-level mixing, so initially we can have something like that, all the n levels, right? Then you will see that as a result of this n-level mixing, one level will go down and the others will again be a little bit higher. This is a n-level mixing. The moral of the story is there is always, as a result of this mixing, there is always at least one bound state which becomes much more bound. This is the overall nature itself of the mixing. So configuration mixing, whether it be 2-level mixing, 3-level mixing or n-level mixing, the moral of the story is one level will always become much more bound as a result of this mixing. So what does this tell us? This tells us that today, just considering this simple case of 2 nucleons, I have now showed you the effect of residual interactions, and that also in 2 different ways. One is regarding the pairing interaction and another is the effect of mixing between pure configurations. So this is the second manifestation of residual interaction. Second manifestation of residual interaction, and this is configuration mixing. Fine. This is actually what is done. So if I ask you in the examination that how do you know residual interaction is there? How can you show using a very simple example? What I am asking is basically I am asking both manifestations. Okay. Don't get confused. I have clearly told you about the 2 separate manifestations. Okay. Any questions? Follow. So you see, this entire argument would not have been possible had I not introduced this M scheme to you. M scheme is very important in understanding these concepts. Okay, see, I have just summarized. You can check the entire online video. I have just summarized the effect of delta type residual interaction. This is the delta type residual interaction. So what I mean to say that there will be interaction only when they come very close to each other, not very long range, no R dependence, no any other sort of dependence. Only when they come very close to each other, they will feel something, and that something is given by this 0, minus V0. This will be attractive nature, so minus sign, right? And only when they come close to each other, they will feel something. So V0 is constant, that something is constant. And only when they come very close, so delta type. We also have modified delta type surface interaction that I am not going to talk about. It's more complicated. But this is very simple. And as a result of this, you can show using basic calculations that there will be a shift in the energy, total energy. And the shift will be proportional to a large number of factors. There will be large number of factors. R dependent factors, harmonic oscillator, if you take basis, those things will be there. But the moral is, along with that, there will be a dependence on a Slabs-Gordon coefficient like this. And this Slabs-Gordon coefficient for large J and capital J values, that means this coupling to J equal to capital J and M equal to 0, this Slabs-Gordon coefficient, this reduces to this form. Now look closely over here. What you see is this. For J is equal to 0, there is no subtraction. This means this entire term is very large. And as a result, you get a very much bound state. For J is equal to 2, there is little bit subtraction. So you get less bound state. For J is equal to 4, there is more subtraction. You get more bound state. So this pairing, splitting due to this. So this is basically the splitting due to our delta type residual interaction. Okay.